Hello everyone, welcome back to another video. I am Radesh BY and today in this video let's have a look at the Shrike Lite FPGA from Vicharak. So let's begin. So Vicharak is a deep tech startup based in Gujarat and they have come up with the Shrike Lite FPGA development board, which is the world's most affordable FPGA development board available at rupees 349. So let's look at the components on the development board. This is the Raspberry Pi RP2040 ARM Cortex M0 Plus dual core microcontroller. This is the WinBond flash memory for the RP2040. And the heart of the development board is the Forge 4 series FPGA from Renaissance, the SLG 47910. It has 19 GPIOs, out of which 4 of the GPIOs are used for the programming of the FPGA via the SPI protocol from the RP2040, and one of the GPIO, that is the GPIO 16, is used on the onboard LED, and the remaining 14 GPIOs are exposed on the board, out of which 8 are in the PMOD style connector and the remaining 6 on the left side of the board. The remaining GPIOs are from the RP2040. The Shrike Lite combines the functionality of a microcontroller development board and an FPGA development board into a small form factor and at an affordable price. Let's look at the full adder implementation by writing the verilog code and deploying the bitstream on the Shrike Lite FPGA. Let's begin. The documentation for Vicharak's Shrike Lite can be found on this link. This is the getting started guide, which is very helpful to deploy our very first bitstream onto the FPGA. So we need a set of tools for this, mainly the Go Configure Software Hub and the Thonny IDE. So let's start with writing our Verilog code. For that, we'll open the Go Configure Software Hub, go to Develop, go to the Develop section, select the Forge FPGA, and select this particular FPGA SLG 47910 RELBB, and give our project a name. So let's keep a name, full adder, and create the project. After the project is created, this will be the project setting. We have to select the first values for all the columns here as given in the documentation, and then click OK. So this is the FPGA code. I can write the FPGA code by opening the FPGA editor or by double clicking on this FPGA code. So this is the Verilog window where we'll write our Verilog code. So the Forge FPGA requires writing the Verilog code in a specific style mentioned here in the Verilog style guides documentation section. So the input pin has to be declared with this particular declaration, IO bidirectional pin, and every output pin must have an output for enabling the output. This is because of the structure of the FPGA. If you zoom in here, for every GPIO there is an input and output, and to select the output there is a mux signal. So this has to be given tied to logic 1. So hence we need 2 outputs in the port list to drive one particular output. So now let's write our code as per the Verilog style guide. Code for the full adder made using 2 off adders. I have tied the logic for sum enable and carry enable. These are the wires for the intermediate logic, and this is the output of the first half adder, second half adder. It gives the final sum, and this gives the final carry. Actually, good practice is to make the modules for 2 half adders and instantiate them, but for this video purpose I have made a single block of code. So we can save this file, and we need to synthesize the file by pressing on synthesize. So there is a warning called network is combinational, so it does not matter, it works, it's not an error. So I have done a setup like this for our full adder implementation. So these are the 3 input push buttons for A, B and C in, and I'm using two LEDs of this 10 LED bar graph LED to represent sum and carry. I have connected the inputs to F2, F1, F0 for A, B and C in respectively, and output of sum and carry as F18 and F17 respectively. So let's put the same in the IO planner. So we have to go to the IO planner where we assign the inputs and output pins from the FPGA to our actual code, we basically link them. So in our full adder circuit, we have three inputs, A, B, and carry in, and two outputs, sum and carry. So we can assign them as per our requirement. So our GPIO2 input is A, our GPIO1 is B, our GPIO0 in is C in. So we have three signals now. So let's assign the output next to the output pins respectively. So the sum is F18 pin, so the GPIO 18 output. So this is the sum, and output enable, we have to assign sum enable. And for carry, we have GPIO 17 output carry and GPIO 17 output enable, carry enable. So we'll save the IO planner and generate the bit stream. So it will take a lot of time. Let's wait. So you can see a few warnings here. These are respect to the clock input. As this is a combinational circuit, we don't need the clock for this. So we can ignore these warnings. And if we go to our folder, the project directory, we'll see the FFGA as the folder. We'll go in and we'll see a look at the build folder and the bitstream folder. We will find 6 files, out of which 3 are binary. So we have to flash the FPGA bitstream underscore MCU because the FPGA on our development board is configured in this mode. So the RP2040 will flash the bitstream onto the FPGA. So we have to use this bin file. Please note that the name of the file is same for every project irrespective of the name. So it is better to you rename it as per your project name. I'll rename it as full adder. Okay, so now let's look at the steps to flash this particular bin file onto our Shrike Lite. So if we are using MicroPython to flash the bin file onto the Shrike Lite FPGA, we need to download the Shrike UF2 from whichever Shrike Lite's GitHub repository. So here is the Shrike Lite UF2. We just download it to our desktop. So once it's done, we have to open up our file manager and we have to connect our Shrike Lite to the computer via the Type-C port by pressing the boot button and pressing hold the boot button, plugging in the USB cable. Then the RPI RP2 removable device would appear. We just need to copy the Shrike Lite UF2 file from our download location to the RPI RP2 folder or the drive. Once it is copied, it will appear as USB drive. So we are done with the UF2 file flashing. So we have to connect our the device to our thonny editor. You have to select the local Python here option in the bottom right corner and select MicroPython RP2040. Then our RP2040 device will be placed here in the left side. So it is very convenient if you have these files available. You can enable it by going to view and clicking on the files. So now we are almost there. We just need to find the bin file which we have to flash to our FPGA. So we'll locate it. It's in the full adder folder, FFGA build, and in the bitstream folder I have my bin file which I renamed it. I'll upload it to the RP2040 device by clicking on this option upload to slash. So this will copy the bin file from my drive to RP2040 device. And we're almost halfway there. We'll just create a new file and we'll import Shrike library. So Shrike library is already built into the UF2 file. So the thing is, we will save this particular Python script in the RP24 device, and once the RP24 device turns on, the Python script will run, will execute, and will upload the full adder bin to the FPGA via the SPI protocol. So we have to use the flash method from shrike.flash, and pass in the argument the file of the name of the bin file. It's full adder dot bin, and we need to save it as uh, main.py. It's very important. It has to be named main.py, and it has to be in the RP2040 device. If it is not main.py, it won't execute. So it's saved. We have the main.py file and the bin file. The bin file is the bit stream enable our FPGA to perform that particular logical circuit, and the main.py will flash that particular bin file from the R2040 to the FPGA. So we just need to unplug and plug in our USB cable and hope the code works. So let's look at the demo. So I just unplugged the USB cable. I just plugged it back in. So this is A, B, and C in, and this is the output for sum and carry. Let's see the truth table for full adder. We are aware of it. So when one of the is high, when one of the input is high, sum is 1. So when both the inputs are high, sum is 0, carry is 1. The same thing here as well. So if all the three inputs are high, A, B, C, sum is 1, carry is 1. Let's verify the same. So let me just press all the button. So sum is 0 now, carry is 1. I'll enable C in. So sum 1, carry 1. So yes, we are able to implement the full adder circuit on our FPGA. And I notice I have not assigned this GPIO 16 as either input or output. So the LED is always on. So I'm not really sure what's the actual reason. But if we do not assign any pin to GPIO 16, it is always in this try state, I believe. So please let me know the issue if you know that. So this was the implementation of our very first Verilog code on the Shrike Lite FPGA. Hope this video was informative. Thank you for watching. See you next time.